So we're back after weeks and weeks of you working on your little class, and hopefully you've done enough so that this little chapter here and the 15% assessment won't be too important to your grade. Let's go at it. Okay, so first of all, what is integration? Now you might say stuff like, oh, it's the opposite of differentiation. Not quite. What integration really is, it's adding up infinitely many infinitely small things. Okay, now you might be kind of shaking your head here, but let me kind of explain this. So take a function which actually doesn't have to be continuous, but we're going to imagine that it is. Okay, and suppose you're interested in between 2 points A and B. You want to find the area. I'm going to just have to look on the next page. Yeah. So what we're interested in finding is the area of this. Okay. So the area underneath it. Now, how we do this is we chop this up into loads of little small pieces. So we chop it up into loads of pieces. Okay. Now we will have these little strips be all of equal width. I'm kind of struggling to draw these up. So can I do a ruler here? So all these are supposed to be equal width. Maybe I should give up now. That last one in particular was callous. So yeah, so you imagine you just put into loads of equal width strips. Okay. And what we're going to do is we're going to estimate, because of course the area under the curve is equal to the sum of the area under the strips. And what we can do is we can approximate the area of the strip by taking a midpoint. So let's say this is the ith rectangle. Take the midpoint xi. This is some function y as a function of x. And we know a and b are numbers that we control. The number of rectangles is a number we can control. And so we can find the midpoint of the ith strip, and we can calculate the height of the function at that point. Just throw it into the function. And we can estimate the area of the strip by using a rectangle with that height. Okay, so the green rectangle, the area of that, approximates the area of the strip. Okay, and what we got? To estimate the area, chop the area into many small areas. Now these are not infinitely many small, are not, can't seem to talk. They're not infinitely many, they're not infinitely many. Here's the problem. Sorry. Adding up infinitely many, infinitely small things. That shouldn't be there. Rusty and they all talking. Okay. So we approximate their height, yeah, okay, and their width. So the width is b minus a over n, where n is the number of rectangles. Okay, so I think we're going to move along now. So what is the area of the rectangle RA? So that was the RI. That was the green rectangle we just looked at. So the area of rectangle RI is the height, which we calculated was f of xi, by the width, which we're calling delta x. Now the width of all these strips / rectangles is the same. Okay, so therefore, if we have n of these rectangles, what is the area of the sum of the rectangles? So we could say something like, if we add up the area of the rectangles from I equal to 1 to n, we get f of x1 times delta x plus f of x2 times delta x plus dot 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 plus f of xn times delta x. That's what we get. So this approximates the area, but if you look at it, it's not a very good approximation. So for example, in this strip here, like over here you're overestimating, over here you're underestimating it. Are those, those over and underestimates going to cancel each other out? Well, you can't be sure, but what you can do is if you take more and more and more rectangles, then the rectangles get narrower and narrower and narrower and narrower and narrower and narrower. And you can show that in a certain sense that the errors get smaller and smaller and smaller. Now there are more and more errors. So even though the things are getting smaller, there's more of them. So maybe it's still bad, but you can show in ways that we don't have to go into that the approximation gets better and better and better the more rectangles you take. Now the question becomes, what happens to the area of these little strips as you take more and more strips? So as you make the delta x smaller and smaller and smaller. Well, the area of the strips, the height, their heights are what are called bounded. I mean, like looking at this graph, the f of xi in the ith rectangle, that's the largest height. And if you multiply that by a width that's getting smaller and smaller and smaller, the area of these rectangles is getting smaller and smaller and smaller, but you're getting more of them. So what you're doing here is you're adding up infinitely many. That's because there's going to be infinitely many, or more and more and more of these rectangles. And they're going to be infinitely small because their height is going to be f of xi by something getting closer and closer to 0. But you're going to add up these infinitely many things, and they're infinitely small, and they're going to add up to something neither 0 nor infinite, the area under this curve. So what do we got? This approximates the area. How do we make the approximation more accurate? Say that the area is equal to the limit as n goes to infinity. So what that does is you have more and more strips, so the strips get narrower, but there's infinitely many of them, add up from I equal to 1 to n. Now what I'm going to do is I'm going to the thing on the right, I'm going to use the sigma notation, f of xi delta x. So this is the same, by the way. So two things are the same. N, which is the number of rectangles going to infinity, is exactly the same thing as the width of the rectangles going to 0. So if you've loads and loads of strips, the widths have to get very, very small. And if the widths are very, very small, there has to be loads of rectangles to get the whole way from A to B. Now, whenever you have do this, so the sum is going infinite, but there's infinitely many things, but the things you're adding up are getting really, really small. And so what you get is this thing here, this blue thing, is actually the definition of the integral. So the integral from A to B f of x dx is actually equal to the limit as n gets very, very big of the area of add up the area of the rectangular strips. I'm not sure how clear I made that. I'm sorry, I'm kind of talking all mumbly jumbly as well. But what I want you to know is integration is adding up infinitely many, infinitely small things. So essentially what you're doing with this thing is you're taking the area and chopping it up into loads of really, really narrow strips. Okay. Now, look, there's one question here. You might say, oh, how do you know that the errors get really, really small? Well, actually what you can do is instead of kind of using the midpoint, you can take a big rectangle where you take the largest value of f on the interval, and a small rectangle, which I'll just paint a different color. So there's the big rectangle. We'll call that the upper sum. And you can also do a lower sum, so you take the smallest value. Now, I mean the biggest height and the smallest height. And what you can show is that for certain classes of functions, so that basically means certain classes of graphs, that as the number of strips gets bigger and bigger and bigger, so the strips get narrower and narrower and narrower, the upper sums using the black rectangles and the lower sums using the purple rectangles get closer and closer and closer together. So you end up saying like, oh, the area is less than 2 and bigger than 2, so the area has to be 2. Okay. So let's see some more examples of these. So distance. So here we're going to have, this should be velocity against time really. So how do you find the distance traveled? So we'll have the car going from rest and doing something like that. Okay, so the question is, how do you find the distance? Well, it turns out that the distance, we'll see this, is this on the next page? No. It's actually equal to the area. Okay, now how does this work? Well, essentially what you can do is you can estimate the distance. So just take a narrow strip of width delta t and take the midpoint as we did before and look at the height of this. So we'll say this is the point ti and the height of this is vti. And so the area of this strip, which I'll call, now it's not the strip because we're going to make a rectangle. So this strip, you see the top is kind of curvy, but just imagine we're using the rectangle. So something like that. So the area of this rectangle, which isn't the strip, but is the rectangle, is the height by the width. Now that's speed by time, which is a little bit of distance. Speed by time is distance. So what you get is an approximation, therefore, that the area in that rectangle is the distance traveled over that little time, delta t. And so you just kind of keep it going in the same way. So essentially you can say something like, some of these are going to be rougher than others. So S is equal to, add up all the little bits of distance. Maybe I'll call this delta SI. Okay. And of course, the delta SI is V of Ti times the little time interval. And if you want to make this more accurate, now let's see what's accurate and what's not accurate. Well, this is an approximation. So the delta SI is supposed to be the distance that's actually traveled between this time and this time. And it's approximated using this thing. So we're going to have an approximation here. But this becomes a better approximation if you take the limit as n goes to infinity of I equal to 1 to n v of t delta t, which is equal to the integral from, well, it wouldn't be a to b here, so this is big T from 0 to t v of t dt, and we say that these two are equal. Okay, so the area under the velocity time graph is the distance traveled. You might have seen that in first year, and of course you know from, well, what we just did is that the area is given by the integral. Now it's still a bit confusing and a bit difficult, but essentially what we've done is, if you make the delta t very, very small, like when you travel a distance, it's made up of infinitely many, infinitely small distances. So this is all this is really saying. So I'll probably go kind of quicker over the next few. So yeah, I'll go just a little bit quicker. So we got a force here, and we're going to have it, and we're going to say how much work is done between A and B. So what we're going to do is we're going to look at a small distance delta x, and we'll take a midpoint xi. So the width of this is delta x. And we'll take a rectangle here. So here you have a little bit of work done between these two distances, and you can kind of show that it's approximately the force at xi by the distance. Now, why isn't it equal? Well, it's because the force is varying a little bit over that little interval, so it's only approximately there. But if you take the limit as delta x goes to 0, So I suppose we're writing as delta x goes to 0, which is the same as saying that the number of strips is very, very big. The actual amount of work done there gets closer to f of xi, which is a bit harder to define now, by delta x. And if you add up all of these things, you get the work done between A and B. And what does adding up all of the f of xi delta x? Well, that's basically, and this is another thing I should have said, so this is a sum, so the integral sign is a big S, standing for sum. And so you have your big f of x, and then this is a capital Greek D, and when delta x gets very, very small, the big capital dx goes to a small dx. So the delta is capital D in Greek. So this is the understanding of how I'm trying to give you an understanding that integration is adding up lots of small things. Okay, we can do another example here. So you got a bar of length L. Oh God, can't draw it to save my life. So this has a length of L. And it's got a variable density per unit length. So this would be over here, you're talking x equal to 0 over to x equal to L. So if we want to find the mass of this, what we'll do is chop it up. And we'll chop it up into loads of narrow little kind of, what would you think about them? They're little kind of fat small cylinders. Okay, so now the density is given per unit length. So a little bit of mass of this thing. Do we need to mess around? I'm just wondering, do we need to... So I was thinking, was the density given as a function of distance along, but it's actually per unit length, which is a different thing to normal density, where it's like density per unit volume. Okay, so we can just find the mass of this little bit of mass. Now the density is variable, so we've got a little delta x here, but that has to be smaller to make this very accurate. So this is only an approximation. Is the density times the distance, and the distance should be delta x. Okay, so if we want to get the total mass, we want to add up all the masses of those little bits, and if we want to make this accurate, we need to make the delta x's to be very, very small, which means we have number of little cylinder things to be very, very small. We're adding up infinitely many infinitely small things, so we're going to have an integral from 0 to L rho of x dx, and I guess this should be like xi. Okay, so have we another example coming as well? So we're just kind of showing the whole time that integration really is adding up infinitely many small things. So what have we got here? Right, so I think we're going to have another rod again. And we want to find the second moment, the moment of inertia. Now, is this about a particular point? It seems to be just about one axis, I think. Yeah, I think it's going to be about this point here. So we just, again, chop it up into loads of little pieces. Okay, and we're going to find the moment of inertia of this little cylinder here. So the little bit of moment of inertia here is approximately, so x will be the distance. Well, we'll call this xi, so this will be a distance xi, and it's like a little point. So the little bit of inertia will be approximately xi squared by delta m, and then the mass is density by, I'm not sure how exactly this works. So you can integrate with respect to m, but that's not going to cut it. So it'll be xi squared. Density is rho of xi times delta x. And so if you want to find the moment of inertia of the full thing, you need to integrate, which means you chop it up into loads of little pieces. So we'll integrate from 0 to the length of the rod. I think we're talking x squared rho of x dx, and hopefully something like that is familiar. Okay, so integration is adding up loads, infinitely many, infinitely small things. Okay. Now, in terms of the actual integrations that I'm going to ask you to do, they're not going to be too difficult. Well, we'll give you just a little strategy. Now, for Math 60/40, you should have a 4-step strategy. So first you use the tables. So just something that's very, very easy to anti-differentiate. Because how do you calculate an integral? Let's remind you, you anti-differentiate. So if you differentiate from here to here, going from the derivative to the original function is called anti-differentiating. So if you want to calculate an integral, you anti-differentiate. So that's something you should remember. And then you do top limit minus bottom limit. So things that are very, very easy to anti-differentiate, like powers of x, sine of x, cos of x, e to the x, all of these things. The others we're not really going to look at, but maybe, well, you might have to do the manipulation where you have to rewrite the thing you're integrating. So one of the things, there's no product rule for integration. So if you've got stuff that's kind of loads of things multiplied together, you might want to multiply it out. So that's called a manipulation. And if that can't be done, you could try a substitution. Now we're going to be looking at 1 or 2 integrals that if you do a substitution, they become a little bit easier. But you'll be able to get by with a manipulation or doing them directly. The next thing on the list would probably be integration by parts, which we won't look at. Now, why the hell are we talking about integration? Well, you've got all these formulas, and the question is, where the hell do they come from? And they come from integration. And we can't have a formula for everything. So even look at that bottom shape. Like, what if you've got some shape that it's not in the books, and you still want to calculate whatever it might be, centroid, second moment of area, this kind of thing. How do you do it? Well, you're going to need integration. Okay. So that's our kind of setup into this chapter.